I would do some quick introduction of the class first. So first, this semester's class will be divided by two parts. So my name is Zhongxing. So I will be teaching the first part of this class this semester. So and the second part will be taught by Dr. Xiaoyu Li. And Dr. Li actually taught the class in whole last year. So I joined in and helped him this semester. So you can see on my screen that all our contact information is listed, including our emails and also where our offices are. So you can also call us. And so our major job is to, of course, teach you. And then we will also answer various questions from you. So my office hour for the first part of the semester is Friday. So 1 hour after the class, I think. So from 2 p.m. to 4 p.m. So during that time, you can just come to my office, knock on my door, and come in and ask questions. Okay, it's just walking. And you can also make some appointment with me. So let's see, oh, I can't come to your office on Friday. So can I just make another time arrangement with you so we can talk? Yeah, fine. That's totally fine. So just email me and see what we can figure out. Okay. And the tutor of this class, which is also in the chat now, is Miss Function and Lam. So she's a postgraduate student in Professor Li's lab. And also, if you have any questions, you can also ask her. And she is also in charge of the tutorial sessions. So you will meet her a lot, again, on Zoom during the tutorial sessions. And she will also answer questions, and you can also make appointments with her if you have any questions or any other things regarding the course, okay? And her email is also here. And so this course is majorly for the chem major, so we have several classes regarding the basic organic chemistry. So what we have here is the Chem 2441, which is organic chemistry 1, and the 3441 is the second part, which is the organic chemistry 2. And together, these two courses will provide you theoretical foundation for the organic chemistry education. And so basically, after you have taken these two classes, you can figure out organic chemistry, but that's on paper, okay? And we have another laboratory course called Chemistry 443, which is organic chemistry lab. And that provides a practical foundation for your organic chemistry education. So basically, you will do experiments and write lab reports, okay? And I would say that there is another course which is called Chem 2442. So that is a more condensed and simplified version of the organic chemistry 1 and 2. So that actually is for not for chemistry major, but it's recommended for non-chemistry or non-biochemistry majors. So that one you can learn all the things that in one semester, which is pretty condensed. Okay, and so this is all the organic concentrated courses we have provided in the department. So you can see now we are at Chem 2441, right? And then you will have Chem 3441. And after that, you can you also need to take the lab, of course. And then you can go you go to the Chem 3442, which is organic chemistry of biomolecules, which also use the same textbook as our course here. And then I think in the year 4, you will have multiple choices to make. So you can go to the advanced organic chemistry. You can also learn integrated organic synthesis, which, by the way, is also taught by me and and also by Professor Pauline Chu from the department. And Professor Chu will be in charge of the lab section of the integrated organic synthesis. And you can also choose the medicinal chemistry and again, also chemical biology if you want to. And so let's just, before we go to the major part of this course, let me just show you what you are going to do or what you are going to come across during the course, okay? So the organic chemistry on paper. So on the level 1, the basic level of this course is that we will teach you that, primary amine, which is shown here, will react with an aldehyde to give a product, and under reducing conditions, which is the secondary amine. Okay, this is a basic level. We teach you this. Okay, then you know what's the product of this reaction, right? So you have the starting material, then you need to write the product. Okay, the second level is that we tell you that we want to make this target molecule, which is a secondary amine. And we also told you that you have to make it under reducing conditions. Now you have to figure out what's the starting material. So because you learned that under reducing conditions, we can make secondary amine from primary amine and aldehydes. So you are supposed to write the structures of the starting material. Okay, that's the second level. So what's the third level? The third level is that we tell you that we want to make secondary amine, which is this structure we want to make. Then we won't tell you anything else, but you have to figure out yourself. Then you have to use your knowledge, your practice, and all the things you have learned in course, in the lectures, in the tutorial session. Then you have to figure out all these conditions and the starting materials, okay? That's the level we ultimately want to achieve. So then if you compare the organic chemistry on paper, which is the organic chemistry 1 and 2 at the organic chemistry lab, so that's the difference. So you may know that we teach you the primary amine reacts with aldehyde, you can get the secondary amine, right? It's very nice and clean. Nothing happened except you writing this on paper, right? But in reality, when you really do these reactions in reality, so you will find that the major product, the secondary amine, is only afforded in 90% yield. So what's the 10% gone, right? What's the rest of the starting material? It seems that there are some minor products, and you have to deal with it in wet lab, okay? You don't have to deal with it on paper or in exam of the organic chemistry 1 and 2, but in the organic chemistry lab, you have to figure out what's the minor products, why the minor products are generated, okay? As I said here, you have to be able to predict and isolate the major product, but you also have to take care of the minor products. So that's the major difference between what's in theoretical and what's in the real lab. So now I'm showing you the course aim here. So basically it's to introduce you the concepts and the properties of all these what we call functional groups, including the alkanes, alcohols, and more advanced like radicals and organometallic compounds, okay? And the most important part of this course is not these functional groups, is that the properties and the concepts of these functional groups. It's not how you memorize it, but it's like you know the concept of properties. So if you know the properties and concepts of these reactions or the properties of these compounds, then even if you forget all of those which have been taught during the class later, but if you remember the concepts, you will be able to get this knowledge back really quickly, okay? And of course, we want you to apply this knowledge to understand chemical behavior and eventually solve chemical problems, okay? So learning outcomes, which is really important here. The first is that you must know how, as a gateway to organic chemistry, how do you describe organic chemistry? How do you describe organic compounds, right? Know the common language. And the second is that this is a nice example actually. So this is a 6-membrane cyclohexane, right? You probably already know that carbon is linked to 2 hydrogens and 2 carbons here, right? But in reality, the organic molecule like cyclohexane doesn't look like this or that. It actually looks like this, okay? That's pretty complicated, right? But we will probably cover this week about the actual structures of these things. So you can know that, oh, in reality, what does this organic molecule look like? And because after all, these molecules are in 3 dimensions. And if you are successful at this, you need to understand the mechanism, conditions, and outcomes of these reactions, like the example I have shown you, right? Or you cannot just memorize that primary amine aldehyde react to secondary amine. You need to know the mechanism. How does this reaction happen, right? Why does it go this way? So why is the secondary amine the major product, or why doesn't it go to the minor product, right? So and what do you use to achieve these reactions? So all these you need to understand by the end of this course. and I hope you do so. And also you need to understand the structure, bonding, and the stability of aromatic, which is probably pretty new to most of you. It's quite different from normal alkenes or alkenes, and so it deals with some more advanced knowledges to understand the structures of these aromatic compound and more complex structures. Okay. Okay, the ultimate goal is that already told you. So if on the exam or in reality, I want you to make this molecule, this secondary amine. So you need to figure out, what do I use? What starting material do I need to buy? And what conditions do I use? So do we have the chemicals of these conditions in the lab? So, and is my way the best way to synthesize it? What's the most efficient way? And how can we save some energy, save some reagents, and blah, 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 like this. So you will need to do some, what we call a retrosynthetic analysis to find out the best way to do that, okay? And this is particularly useful if you want to join the lab in the future. So, and when you join an organic chemistry lab, your supervisor would expect you already know most of this. And although you will learn more advanced knowledge in the lab settings, but this is what we show you that can prepare you for your real practicals in the lab. Okay. Okay, how to study organic chemistry? So of course, attend the lectures. Okay, and for lectures like Tuesdays, so like today, it's gonna be double lectures, and on Friday it's a single lecture. Then all of them are done via Zoom. And I want to say that all of the recordings of the class will be uploaded 1 to 2 days after the actual live sections. But some of you already asked me, so what's the it's like since the recording is going to be uploaded, what's the point of the live section? So the thing is that I want you to really have some kind of interaction. So there will be class practice during the live sections. And I hope that, and also I will make some like instant announcement during the class. For example, I would say, oh, the problem set is open, you can go do it now. But the video is uploaded only after 1 or 2 days. So if you want to really keep pace with the course, the progress of the course, you really need to attend the lectures, because there are some instant announcement, and there are some practice, and there are some interactions. Okay, and you need to actively listen to what I explain about some problems and practice with me during classes. So what I want to ask you is that always have a pencil or pen ready, and always have a blank papers, so you can draw with me. Okay, I draw something, then you follow me, or we draw together. Okay, so this will be explained in detail later. Okay, the textbook. So I've actually read this textbook, which is really good, and it's highly recommended that you buy one, because both of three, I think that's more than three. So both 2441, 3441, and 3442, three theoretical classes will be using this book. And the difference is that we will only cover the chapter 1 to 13 in the first part of this semester. No, in this semester, and the next semester or later, the other course will cover like chapters 14 to 20. And chapters 21 to 26 deals with some biomolecules, more complex ones. So it will also use this book, okay? And another thing is that please do problems, okay? So there are two type of problems. One is that there is assigned problem sets, okay? Some of them are for credit, some of them are not for credit. Okay, and you can also see on Moodle, you can see the course information sheet, and you can find more information about this problem set, the due date, something like that. And also another problem is, although that's not for credit, but it's really important, okay? So you need to do the in-chapter and end of chapter problems on the book. And the solution guide already has the answers for you to, to learn and to see whether you are right or wrong. And luckily that all these solutions and end of chapter problems are available on Moodle. So we have cut these pages out and scan them, or we just put the PDF of these problems on the Moodle. So you don't need to go to the book. You can download them on the Moodle and do it. And there is answers attached to it. So you can easily know whether you are wrong or you are right. And attend the tutorials. So basically those problems you are going to solve in the tutorial sections are provided by the teachers, which is me. So, and I would try to make these problems very very similar to what I'm going to put on the midterm and the final exams. So attending tutorials really helps you to understand the problem, and to some of you, more importantly, help you prepare for the exams, right? To get high scores. So please do attend. So there are several sessions you can choose from, which are 4 sections you can choose from. So I heard from Function that some of you may have some general time clash with these tutorial sections. So for example, if the whole class have some some other classes you have to attend to during Wednesday and Thursday at 5 to 7. So please do reply to the tutor, and you can email her or just mention it in the chat sections. So if you have any general time clash, so we can change the time of the tutorials. But if it's only personal issues, then if it's not a general time clash, then we probably will keep this time for the section. And also all these tutorial sessions are on the Zoom. So you have to attend virtually, and you don't need to come to campus on that. And also for the Moodle, we use Moodle a lot. So you can download the lecture notes, and I will upload it after the class. And there is online problem set, as I mentioned, and there are additional resources, and there are important class announcements. So I will show you the Moodle later to guide you around the different sections of the Moodle. Okay, so basically you have to attend the lectures, read the textbook, and go to the tutorials, do the problem sets, and visit Moodle often or get your information from Moodle often. And you have to attend the midterm and the final test, of course, if you want to pass, right? Okay, so, but however, learning organic chemistry requires memorizing a lot of stuff. So you can see the chart. So I have learned organic chemistry for more than 10 years, I think. Yes. So basically, if you point out a number of this reaction to me, I can tell you what's the reaction and how does it go. Okay, what's the mechanism of that? But you don't, right? Most of you don't. So that's why you have to learn, and I have to teach you, right? So how to help you to master all these reactions after all the theoretical classes and the lab classes. So that's something we have to figure it out together. And the most important thing on your part is that not only you have to do all these tests or attend the classes, you have to be diligent and patient, okay? So although I think organic chemistry is fun and not that difficult, most of the students, like when I was in US, most of the American students think, oh, OChem is probably the most difficult, like basic chemistry classes. And so just you need to be diligent and patient, okay? It's not that easy. Okay, maybe for you it's not easy at all. Okay, so syllabus. So I am going to cover chapter 1, 2, 3, 4, 5, 6. So until the alkynes. So I will also teach you alkynes. That's the first part of this class. Okay, and after that, Dr. Lee will take over. And these are two the most important date, which is October 9th and November 13th. Okay, I want you to keep this in some safe place and remind yourself of this date. This is a midterm, okay? You miss one of the midterm, you are screwed up, okay? And so the midterm of the first midterm will be October 9, which will cover until the alkynes. So chapter 1 to chapter 7, okay? Which is my part. And I will also take an active part in making the final exams. And so the final exam now accounts for 55% of the cost, okay? So apparently the faculty doesn't want all of your percentage of evaluation put on final exam. So that percentage, 55%, is already decreased from the percentage of previous semesters. So you nowadays it's hard for you to fail if you fail the final exam, okay? And so two midterm is 30%, which means 15% each. and 3 assignments for credits, which is 5% for each. All right, so before we go to the content of this class, I can show you the Moodle. Okay, so this is the Moodle. Let me see. Okay, where is the chat? Okay, so on the Moodle, you can see a news announcement, right? And once I put a news announcement here, it will automatically send you some emails about it. So don't worry about that. And you can sign up for tutorial here, which is the time is listed here. Just click this, sign up for tutorials. And I think some of you have already signed up for that. So that's good, very proactive. Okay, and then we have assignments and exercise. So you can see the nomenclature for organic compounds, not for credit. You can just do this. And some of the problems will be only available after a certain period of time. And I want to show you some, so on this column, you can see the additional resources. Okay, then we have 7 videos about nomenclature, and we have also some other information that you need to make you better, okay? And for the lecture notes, I will upload it once we are done every classes, and the recording of the class will also be uploaded, all right? So that's for Moodle. So I think we can now go to the major content of this class. Okay. All right. So before we go to the advanced part of this class, we will first review some of the important concepts you may have come across during your previous classes. Okay. So the learning outcome. So I actually combined these 3 chapters together as together. So first is that you have to review the acid-base properties, review bonding, something like that. Actually, I will teach you how to do that, okay? And then review functional groups and review nomenclature and review all these forces, chemical properties, something like that, okay? So because this class is not face-to-face, so you can always ask and answer questions using the chat function, okay? Mr. Lam will monitor the chat and answer your questions. And you are also recommended to open your video cam, so I will not force you to do so. And because it really helped me get touch of your reactions and really adjust my pace of class. And also if you think the class is too difficult or too simple, too fast or too slow, just let me know, okay? And if the majority of you thinks, oh, the class is too difficult, could you slow down a little bit? I will do that, all right? Okay, so what you have learned in general chemistry. You may already have learned that atomic and electronic structures, ionic covalent bonds, and all these orbitals, hybridizations, molecular orbitals, okay? I will not go into detail about these, but these are really, these are actually reviewed in the chapter 1 of the book, and you can easily go there and read through them, okay? And so what we focus in organic chemistry, organic chemistry. So what is organic chemistry, right? So chemistry of organic compounds, okay. So now we have a compounds, so organic compounds. So you have learned some chemistry, right? So you know that chemistry is all about structures, properties, and reactions. So we are going to learn these about the organic compounds. But how do you define organic compounds, right? So the organic compounds is compounds based on carbon. So in summary, we are going to learn the structures, properties, reactions of compounds based on cameras. Oh, not cameras, based on carbon. Okay, so then you will ask, so why is carbon so special, right? So you can see the chart here. So for the Earth's crust, okay, the carbon is only, it's too much. This carbon is only 17th in ranking about the abundance, okay? And actually the oxygen and the silicon and the most abundant elements in the Earth's crust. Why? Because basically it's rock, right? Silicon dioxide is just everywhere in the Earth's crust. But if you look at the human body, the carbon's ranking actually increased dramatically. Now carbon is actually the number 2 in abundance. And the number 1 is oxygen, number 3 is the hydrogen. Again, why? That's a common sense, right? Because most of your human body is composed of water, right? But the carbon is number 2. So actually carbon exists in almost everything in your body. So if you look at these structures, so you have a glucose, which is a sugar, right? You have fatty acid, basically all these carbons forms in a chain, and unsaturated carbons, so these are fatty acid. And you have RNA, DNA, and the base pairs, which is also, most of them are carbon. And you have amino acid, which is the carbon backbone of these. Okay. So carbon is also everywhere in modern industry. So not only does the nature use carbon to compose the human bodies or biologic systems, but our human beings during industrial age also use carbons a lot. Okay, so this structure is which is called Humira. So this is the top-selling prescription drugs #1, the best. Okay, it generates billions of retails every year. So you can see it is actually, so this structure, you might learn it in the biochemistry, it's antibody. So it consists, a single antibody of this consists of more than 6,000 of carbon atoms. So if you look at the #2 prescription drugs, it's actually, it's called Eliquis. It's an anticoagulant. So it's also carbon-based. You can see carbon, it has 25 carbons in it. You can see basically all the backbones are composed of carbons, right? So because the human bodies or the biologic system is made of carbons a lot, it makes sense that all the drugs are carbon-based, right? Because you want it to interact with your biologic system. So, but also for some material science or some daily stuff you use, it's also composed of carbon. So this is a nylon shirt, right? And if you look closely, you can see the knitted nylon. And if you look more closely, it's a nylon fibers, which you can see it from the scanning electron microscopy. And then if you look closely in the molecular level, so it actually is composed of this polymer monomer, which is called nylon 6. And actually it's generated, so people make this in 2.1 million tons per year. And this eventually goes to your shirt. So then, why carbon? So why does biologic system use carbon a lot, and why does the industry use carbon a lot? It's because two things. One is diversity, the other is stability. So I'm going to show you why diversity is really important factors in making carbon abundant in all these systems. So you can see a part of the periodic table here. So lithium, boron, carbon, nitrogen, oxygen, fluorine, right? And then atoms to the left of carbons, like lithium, is prone to give up electrons. You probably know that lithium ion is very common, right? And the elements right to the carbon actually is prone to accept electrons. So fluoride is a very electron withdrawing element, so it's more stable as a fluoride anion. But carbon is different. Carbon is in the middle of them. So that makes carbon a really friendly atom. So it shares electrons. So when it shares electrons, it can share with nitrogen, and it can share with oxygen, and can share with fluoride, right? So you have different functional groups that are based on the sharing power of carbon. So you have alkanes. When you share it with nitrogen, you have amine. When you share with oxygen, you have alcohol. And then you have also different kinds of alkyl halide when you share electrons with fluoride, chloride, iodide, something like that, okay? So besides being a friendly atom, carbon can form up to 4 bonds, okay? So that's quite different, because for the halide here, it can only form 1 bond, oxygen 2, nitrogen up to 3, carbon up to 4. So you have more room to share bonds. Not only you can share bonds with different atoms, you can share more bonds with other atoms, okay? And then this concept you probably already learned is a hybridization. So not only the carbon share bonds with different elements and share more bonds, it can, change into different hybridizing state. So in that case, you can have different bonding status. So for example, you have sp hybrid orbitals, which is give you CC triple bond. Now you have alkynes, right? And then you have sp2 hybridized orbitals, which gives you ethylene, right? And if you, so if you look at these two structures, actually they are very different. So if I click this, okay, so the alkyne is actually linear. So you can see this structure, right? I hope so. Okay, and so this is linear. So, and if you look at the alkene, it's not linear. It's a plane, right? It's 2D structures. So carbon, it basically it's composed of the same element, but it's just one is linear and one is planar. So really nice. Okay, and then we also have, which is very important in organic chemistry, the sp3 hybridized orbitals. So now you have 4 substitution, and this is, you might already know, tetrahedron, right? And then you have 2 planes of this molecule. So if you look at these hydrogen, carbon, hydrogen, this is one plane, right? And this hydrogen, carbon, this hydrogen is another plane. And it has a dihedral angle of 90%. So this plane is actually can be rotated 90 degrees to another plane, okay? And this is the most abundant hybridization state of carbon. And based on this, you can, if you have put 2 carbon together, you now have ethane. And you have put 6 carbon together, you can have the cyclohexane. And all of these we will learn later, okay? And so just to make it complete, you can see the methane structure here. Now it's a 3D structures, and you might have learned via CPR that all these bonds are equal distance to each other, and the plane is like, so this is 3 plane, this is 1 plane, this is another plane, okay? We will go into detail about that. Okay, so that all these are showing you that carbon did have more diversities, okay, and stabilities. Okay, common question is that silicon is abundant in Earth's crust, right? And it's in the same group of carbon, so it can also form 4 bonds, right? But why not silicon? So why are we not silicon-based human beings? Okay, made of all of them made of silicon. The thing is that although the silicon can make 4 bonds like the carbon, and the sp3 silicon is really it's also stable. But it's not stable. What's not stable is the silicon-silicon double bond and the silicon-silicon triple bond. And all these unsaturated motifs are really common in biologic systems and in materials. But silicon can only form a single bond, and all these are very unstable. So you don't want to build a biological system, right, like human beings with silicon, and then you just break off, right? No, but carbon can do that. Carbon have all these hybridization and all these structures. Why? So the common reason is that silicon is much bigger than carbon, and you can see the radius of this. And the rule of thumb is that the larger the atom size, the weaker the strength of bond. Okay, so how I help you understand this is through a comic strip. Okay, so you can we have 2 T-Rex meeting each other for after a long time, really happy, and they want to shake hands. No, they can't, because why? Their heads are too big. Okay, so that really illustrated the situation, because the silicon is too big, and the orbital overlapping between 2 silicons is really hard. Not to mention you have to share 2 bonds together. So that makes you really unstable and create a lot of unnecessary misunderstanding like this here. Okay, just keep this in mind. Silicon cannot be used for biologic system because it can only form a single bond, and double bond silicon-silicon bond is really unstable. So it's triple bond. All right. And okay, so a brief summary is that I listed all these points here. Carbon shares electrons and forms small bond and different hybrid orbitals, and carbon-carbon bonds are relatively stable. Okay, so that's why in biologic systems, nature can make so complex structures based on carbon. For example, this which we call a platoxin is isolated from some plants in the Hawaii. Okay. So when you go swimming in Hawaii, just if you see something beautiful, don't touch it. It's probably toxic. Okay, and you can see all these complex structures with different bond formation, and so if you are interested, you can figure out how many carbons are there, and how many sp3 and sp3 carbon, how many CO bond, CN bond, and what's the longest linear carbon chain. I actually counted the number of carbon chain here. It's more than 100. So I won't do this here because it's just a waste of time, waste of the valuable time to give the lectures. But if you are interested, Just go figure it out, okay? And so a very inspiring question is that, do you think if human beings can make this? Okay, we know that nature make this, make these beautiful plants with these structures. And do you think human beings can synthesize this or not? So if you are interested, again, you can Google the total synthesis of plastoxin to find out. It's a very inspiring story, so. All right, so we want to learn the structure, property, and the reactions. We must go to the structures first. Okay, so how do we draw organic molecules? So you probably are familiar with this way, basically very, I would say, elementary style. So you have propane, you draw all the hydrogens, you show all the bonds and atoms, right? And in this class, don't do this, okay? Please do not draw this in exam, your assignment, or anything else. Just this is really abundant and really complex and waste a lot of your time and my time. Okay. A simpler version, which is called a condensed structure. You are also not recommended to draw like this, but if you draw like this, I will accept it. Okay. So the guideline is that bonds are minimized or not shown. So you don't draw this. You just CH3, CH2. Okay. So atoms and groups are gathered on carbon. So H3 is put next to the carbon. You don't draw like this. And the groups on carbon are shown hanging off carbon or in brackets. Okay, you can draw one bond and you put the CH3 here, and you can draw a benzene like CH, 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 and you can draw ethanol like this. This is acceptable, especially you are in the initial stage of learning organic chemistry, okay? If this appears on your exam, I will accept that, but the best structures I want you to draw is called skeletal structures. Okay, it's recommended in drawing in class assignment and exams. Okay, so what's the point here? So bonds are shown as lines. Okay, so you don't see any carbon atoms here because carbon atoms are not shown in skeletal structures. So I assumed to be at the intersection and the end of line. So if you look at these structures, right, intersections, this one. So we assume that there is a carbon here. So at the end of the line, one end, two end, so 3 carbons, okay? Hydrogens are carbon atoms not shown. So you don't see any, you don't see any hydrogens here, okay? All eliminated. So assumed to fill the rest of tetravalency. Okay, you have a carbon here attached to one carbon. So the rest of the tetravalency is what? 3, right? So if you draw like this, we assume that this carbon has 3 hydrogens attached to it. Very convenient, right? It's just to save you a lot of ink. And but atoms other than carbon and hydrogen are shown. For example, if you draw ethanols, you have to write the O and the H on the O because that's not carbon, okay? And for the benzene, you don't have to write the H anymore, right? It's just double bond, double bond, double bond. And for this one, 2-methylbutane. So you assume that this one is a carbon, and the carbon has 3 carbons on it, and the rest of valency is 1 hydrogen, which is assumed to be here. Okay. So one thing is that you can, for example, for those 5 carbons here, you cannot just draw a line and say, "Oh, Dr. Huang, I meant the 5 carbons." It's ridiculous, right? How can I know you have 4 carbons? So for the carbon chain, you have to do the zigzag. Why do you do the zigzag? Is actually the real structures of these carbon chain is zigzag. So for example, you have a 5 carbon. So it's actually look like this. If you have a 2-methylbutane, it's also zigzag, right? So you cannot on your exam draw this and expect me to know, oh, how many carbons I did. This is just wrong. And also these structures. So you have to draw like zigzag, up, down, right? 3 intersection, 2 end, 5 carbon. I hope this is understood. You have to be crystal clear about this. Otherwise, there's no way to proceed. Okay, to help you practice this, I know maybe some of you already know this, how to draw like these structures, but to help you practice on this, so you can take out a pen and draw with me, and to simplify these structures into skeletal structures. Okay, I'm going to open this. So you can see this screen right now, right? So because if I use this screen, I can better show you how I draw structures. Okay, so just did everybody have a pen? Okay, just start drawing with me, okay? It's fun. Okay, now we have an alkyne, right? Because all the hydrogens should be eliminated. So what you draw is 3 bonds. Okay, nothing more. Then we have a chain of 3 carbons here, and you have to draw it in a zigzag version. So 1, 2, 3. Okay, and then we draw this part, which is a double bond. You don't have to draw the hydrogen here. The bond drawn, and now we draw this one because it's not a carbon. You have to show it. It's chloride. And then another carbon chain, but it's has a side chain on it. Okay, and you just poop and the side chain here, and then we have a double bond with 2 carbon. Okay, and now we have some oxygen in the way. Okay, so because it's oxygen, you have to draw the oxygen, and have a nitrogen besides it. And you have 2 carbons, which is zigzag, and you have another carbon, and you have oxygen. You have to draw this, and the oxygen is attached to a carbon. You don't need to draw this, and the oxygen, the carbon, this carbon has a double bond on it, and then a carbon with a double bond O, right? And then nitrogen. Now, at this moment, you see the nitrogen is attached to 5 carbons, which is a ring, right? So you can draw the ring first. So on the ring, there is a carbonyl, and these 2 carbon forms double bond, and there is a carbon here. And you don't need to show the carbon, and you need to draw the double bond, and you need to draw the double bond O. Okay. So that's how you draw the skeletal structures. So I will put this on the. I will put all these class practice on the Moodles also after the class. So with my drawings on it, so you don't need to worry about. All right, let's close this. Back to the slides. Yeah, I'm tired too. Okay, so we need to after this practice, so I will show you how to draw 3D structures. So because as I told you, the organic molecules are mostly in 3D dimensions, right? So especially methane, you have and I already showed you the structures. And how to draw the tetrahedron carbon with sp3 on it, so which is a way to represent a 3D tetrahedral center in 2D, which is on papers. And especially when you learn stereochemistry later in the course, you will have to do that. So first, so what we want is we want to draw these structures on 2D. First, you draw a V with an angle of 120 degrees. This represents 2 bonds that are on the paper. So you draw like this, and this is assumed to be on the screen, okay? It's a 2D structures. Then you draw a bold bond with the center pointy, and this represents a bond pointing out of paper towards you, yourself, not me, you, okay? So this bond, you can see it's bold, and the pointy one is on the center, not on here. It's on the center here, okay? So this bond is pointing out of screen to you. And then you draw a dashed bond from the center with a pointy end on the center also. And this represents a bond pointing out of paper away from you. So in this case, you have this dashed bond with this pointy end here and this big end here. So this bond is not on the paper, it's pointing to the back of the screen, okay? So the same way that you can draw another angle like this, and you can draw a bold bond here, bold bond here, bold bond here, and then you can draw a dashed bond here, dashed bond here, okay? Then they represent the same molecule, but just this is like you rotate some angle to here, and you keep rotating like this. Okay, some things to keep in mind. So the plane V, this big V, has a larger angle than the bold dashed V. So this angle is smaller than this one. So it's this, okay? And do not cross each other. So the red thing does not cross the blue thing, okay? So there are some wrong drawings I don't want you to have, okay, here. Why is this wrong? Why is the first one wrong? Because the blue angle, or because the plane V has a smaller angle than the dashed bold V, right? This is wrong, okay? And this is also wrong because this angle is smaller than this angle. So the plane one should be larger. And this is wrong because why? Because the red and the blue cross each other. So the plane V cannot cross the bold dashed V, okay? I hope you, so there is only way you can be good at this, be good at drawing is like just practice, right? Okay. Okay, another special case about drawing the sp3 tetrahedron carbon is if you want to draw the carbon with hydrogen atoms, okay? So we assume that you have a hydrogen carbon here, right? So the standard way, as I pointed like in the previous slide, is draw like this. But it's too complicated because when you draw the skeletal structure, you have to omit the hydrogen, right? So when you omit the hydrogen, do this. You can draw up the rest of the substitution here. So without hydrogen. And then now you see it's like the same angle, 120 degrees, right? So this is still sp3 tetrahedron carbon, but the hydrogen is not shown. And the bond, although it's drawn at 120 degrees, but it's just a drawn, so it's not the real angle. The real angle in sp3 tetrahedron carbon is 109.5. Okay, you just draw like this, but this actually represents structure like this one. Okay, so after we show you how to draw the molecules, then we need to how do we communicate with each other and let you know that I'm actually talking about some molecules, right? So we name them. So how do we name them is first, we name them by functional groups. So you can see the definition here. So a functional group is a certain group of atoms or bonds within a compound that is responsible for its properties and for its chemical reactions, which means the same functional group will react in same fashion, undergoing the same reactions or similar reactions, regardless of what the compound, the functional group is in it. Okay. So what it means in deeper is that if in the organic chemistry course I teach you that ketone can be reduced under certain conditions to alcohol, so you are expected to know that different ketones in different molecules will react in a similar fashion. So that means like if we use this ketone and this cyclic ketone, you get a reduction to become an alcohol in the same way, okay? If you encounter such a complex molecule, but still this is a ketone, so it should react in the same way to become alcohol, okay? So this, you have to keep it in mind. So, and this is the foundation of introducing chemical reactions to you, because there are like millions of reactions in the world. I cannot teach you every single one of them to you, right? I can just show you a general trends, what I call the principle and the properties. Then you are supposed to, go from there, understand the rest of the similar functional groups reactivity, okay? Okay, then I think, yeah, let's just finish this part first. So second, we named the organic molecule use the IUPAC rule. So you probably already learned some IUPAC rule in your general chemistry. So what it means is that an organic compound and the IUPAC rules have a unique and unambiguous name, okay? And compound has only one name, and the one name represents only one compound. So that's what rules are for, right? So some important information about nomenclature here is that I'm not going to talk with you in detail about how to name a compound, but this is somewhat like a self-learning module, and there is seven videos made by Professor Chu about how to name organic compounds. And the problem set 1, which is not for credit, is a Moodle drill that composed of, I think, 10 questions that it's all open only for a limited time. It's a really good opportunity to practice on them. And although this is a self-learning module, it will be tested in midterm 1, but very small amount of the midterm 1 will be on nomenclatures. And the difficulty of these questions will be similar to the Moodle drill. So I sincerely recommend you to do the Moodle drill and to watch the 7 short videos. And although you can say, oh, I can give up the 5% of this nomenclature part, I suggest you not, right? You want every point at your side, okay? And so some general principle is first you decide the functional family of the compound, then you determine the parent chain, then you determine the priority of the groups, and you assign numeric order to all different groups, and you want to make sure the order it has the lowest numbers possible, right? And then you name the substituents and order them according to alphabetical order. Okay, just be sure to watch those videos on Moodle. Okay. You don't want to lose any points in midterm 1. Okay. And okay, I think we will like pause here for 5 minutes. Okay, we have the class until 12:20, right? So it's so we will be back on 11:26 in 5 minutes. Okay, just freshen up and have a small break. Okay. Okay, is everybody back? Yeah, I haven't talked that much since after I came to Hong Kong, so especially in English. So we will continue with the class. Okay, one more time. Please watch the videos by Professor Chu. Okay, and so I'm going to slightly touch on some of these naming rules here, okay, just to let you know what's really important here, okay? So we have a list of alkane and alkyl names, all right? So you have a methane, which is a CH4, which is called methyl group, which is a CH3, okay? But if in the rest of the class or in exam, if we normally can use ME, which is short for methyl, right? Or in British English, miso. Okay, so if you see this means CH3, and for the ethyl here, ET, which means C2H5. Okay, and these names like propane, butane, like nonane, it's really important. It's really important to remember, and and because they serve as a foundation for nomenclature, because a lot of, when you name the compound, you want to look at the parent chain, and the parent chain is usually composed of these alkyl groups, okay? You need to keep these in mind, and be sure to keep all these names. Memorize them, okay, memorize. And when we speak of alkanes, there are some very, very important classification of substituted carbons, okay? And for example, if we say this carbon is a primary carbon, what we mean is that this carbon is bonded to one other carbon, which is R. R also stands for substitution, okay? It can be any group, but in this case, it's substituted to another carbon. The R is another carbon. So the secondary is 2 other carbons, the tertiary 3 other carbons, quaternary 4 other carbons, okay? So this quaternary carbon we usually call all carbon substituted. So, and so when it's a group, it's an alkyl group. It's linked to someone here. It's linked to someone, and this one has 2H and is bonded to one other carbon, which is R. So that's a primary alkyl group. Same. You have secondary carbon. You have secondary alkyl group. Tertiary carbon. Tertiary alkyl group. You don't have quaternary alkyl group, okay, because the quaternary alkyl group, the quaternary carbon is already substituted with 4 carbons, so there's no group. So okay, you can't say there is a quaternary alcohol. That's not possible, okay, because the quaternary means the carbon is already substituted with 4 carbons. Okay, keep that in mind. And a little practice here. So you can see this structure is tetradiol. Yeah, something like that. It's isolated from a tree. So this benzene has a sp2 carbon, so we don't need to classify it right now, okay? And then we have now you have to, I will lead you to do that. So which is quaternary carbon, tertiary carbon, secondary, primary. So the rest of carbon, how do they belong, okay? So let's go one by one. So this one is connected to 1 O, right? 1 O, 1 hydrogen, 2 carbon. So that's secondary, right? This one, 2 carbon, 2 hydrogen, because 2 carbon, secondary. This is same, secondary. This one, 1 carbon, 2 carbon, 3 carbon, 4 carbon. So this is quaternary. So this one, primary, because only connect to 1 carbon. And this one, secondary. This one, 3 carbon, 1 hydrogen, which is a tertiary. This is a quaternary because 4 carbons, right? For this one, 3 carbon, it's tertiary. This is primary. This is also primary. So it's quite simple, right? Okay, and then for amines, it's it's also the same. So you have a primary amine, which is bonded not to carbon, but to substituent, a general substituent, not only carbon, okay? If it's substituted with 1 substituent, so it's called primary, and then you have secondary, 2 substituents, tertiary, 3 substituents. When you bond it to 4, because it's now it becomes a salt, right? Because the nitrogen in its neutral form can only connect it to 3 other substituents. Okay, now you have a quaternary ammonium compounds. It's bonded to 4, but it's also have a positive charge on it. Okay, then you have these 4 compounds. So the first one, which is from I don't know how to pronounce this. Anyway, it's a cactus. Okay, it's poisonous. So it has 2 hydrogen, 1 substitution. It's a primary, and this one 1 hydrogen, 2 substituents. It's secondary. This is tertiary, and this is salt, which is the nitrogen is connected to 4 substituents. So it's quaternary ammonium compound. So an interesting thing is that you may recognize nicotine, right? It's in cigarettes, right? This is a poison hemlock, and this is isolated from the mushroom. So these are all very poisonous. So basically, if you found some nitrogen compound in the nature, it's there is a high chance that it's poison. Okay, just keep that in mind. So I don't know whether you will use this knowledge or not, but just keep it in mind. And okay, some different classification is listed here, which is deals with some alkyl halides and alcohols. So when we say it's a primary alkyl halides, it means that the halide X, which is fluoride, chloride, bromide, or iodide, is linked to a carbon. Okay, so the classification is based on the carbon's classification attached to the halide. Okay, if this carbon is primary carbon, we call this alkyl halide primary alkyl halide. So again, if this carbon is a tertiary carbon, we call it a tertiary alkyl halide. So again, the question is there any quaternary alkyl halide? No, right? I just told you so, because a quaternary carbon is already attached to 4 carbons. There's no way it's also an alkyl halide, okay? And the same with alcohol. You have primary alcohol, secondary alcohol, tertiary alcohol, no quaternary alcohol, okay? Don't make this mistake. And this type of classification is also applies to hydrogen. So if you have a primary carbon, you have a primary hydrogen. If you have secondary, you have secondary, right? It's quite simple to understand. Now, why these classification? Why do we need to figure out how is this a primary carbon, a primary hydrogen, primary alcohol? So it's because while the same functional groups have similar reactions, so different subgroups of these functional groups show different extent of reactivity. For example, you probably will learn this later. If you react with this compound, which is 2-methylpentane, react with bromine in light conditions, you will get bromination products. So one of the CH bond will be replaced by a Br, bromide bond. Okay, this reaction happens, majority of this reaction happens at the tertiary CH bond here. That's why we want to learn what's different the classification of these bonds, because for example, this reaction only happens on tertiary. So when you have this condition and your starting material, you will try to find okay, this reaction is exclusively or majorly happens at a tertiary CH bond. Let's find the tertiary CH bonds in the molecule first, right? And also, even the same subgroup of functional groups in different parts of the same molecules can have different reactivities. For example, you have this biological molecule called androstenedione, okay? And you have a 2 ketone here, right? And the 2 ketone can react very differently, okay? It can under some reactions, it can react with the less bulky ketone. In some reaction conditions, it reacts with the bulkier ketone, okay? So this is really more advanced stuff, and probably it will take you like 3 to 4 years to start to get in touch with this stuff. But if you are really interested in these topics, you just Google site selectivities controlling organic reactions, which is really stand at the frontier of the organic synthesis. Okay, just for your fun, or if you are interested. Okay, so in reality, okay, we don't use IUPAC names a lot. So especially, for example, in my lab, I don't talk to people with IUPAC names. Okay, that's really abundant. So they are not frequently used. And many organic compounds are referred by their common names. So common names is like tradition, we call this thing this name. Okay, for example, acetone, which is a ketone, and folic acid, we don't name it using like 20 words. And the toluene, we don't say, oh, could you hand me the 1-methylbenzene? No, which is called toluene, okay? Xylene is a dimethyl benzene, which is a benzene substituted with 2-methyl, okay? We don't call them, oh, today I'm going to use some 1,2-dimethyl benzene as my solvent. No, we just say, today I'm going to use xylene. Okay, and then in more advanced studies, like in organic chemistry literatures, researchers normally don't use IUPAC names. They use common names. They also just refer the structure with a number, okay? What does that mean? So you can see this, I actually get it from a recent organic chemistry paper. So you see they mark their structures with a bold number, right? 23, 29, 28, right? So in their description, they will say, oh, blah, 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 sufficient to elicit the formation of 28. Then you know, oh, where is 28? Okay, they are talking about this molecule, all right? And at 3 equivalent of hydrogen of 29, okay, they got this. You have to look at the figure to figure out what's the molecule they're talking about. This is quite like a simplified, right? So if you just name this molecule, it will be like a very long name. Then a quarter of your papers will be names, okay? So you don't want that. Okay, so after the structure part, so we will start to talk about properties. So I want to review some concepts you have probably learned in the general chemistry. The first of them is bond strength, okay? So we have a triple bond here, double bond here, single bond here. So you probably should know that the triple bond is the strongest bond, which is also the shortest, while the CC single bond is the weakest and the longest. So there are two general trends you must keep in mind. As the bond strength increase and bond length decrease, so weakest, which is the longest, strongest, which is the shortest, okay? Because if the bond strength increase, it normally means there are more bonding and electron sharing. And if you share more electrons, your bonding is stronger, right? It's like shaking hands with another guy or with your classmate. If you have 2 hands shaking, so it's strong, but it's breakable, right? But if you have 4 hands sharing, it's harder to break, okay? So, but you must avoid one misunderstanding about this is that you see a double bond here is stronger and shorter than a single bond. This is a correct statement, okay? But you know that the double bond has pi bond in it, right? So, but you cannot say a pi bond is stronger than a single bond, than a sigma bond, because when we talk about double bond, the double bond is actually composed of one sigma bond and 1 pi bond, okay? They combined to be stronger than a sigma bond, okay? So and pi bond is actually weaker than sigma bond. So just keep that in mind. Don't make this mistake, okay? Okay, then I'd like to talk about some difference between s and p orbital. So s orbitals are balls, right? So it's closer, right? The s orbitals is closer to the nuclei, and it's non-directional. What do I mean? Non-directional is that it's a ball. The ball is like all directional, right? It's not like an arrow at point to one direction. A ball is like there's no left corners. It's a ball, right? And but the p orbital, the difference is that the p orbital is farther from the nuclei, so it's in the outer side of the element, right? And it's directional because it's not a ball, right? It's like a stick pointing to something, okay? Pointing to this or pointing to that. Okay, what's the effects of these difference? Is that if you compare CC bond and the CH bond, the bond strength is different. So the CC bond is sp3, sp3. The CH bond is sp3s. So you have more s characters in the H and in this bond. So that means because the S is closer to the nuclei, so that means the bond is shorter because they have to be closer to each other, right? The bond is shorter. So that means the CH bond is actually stronger than CC bond, okay? Okay, understandable, huh? Okay, then if we compare different types of CH bond, so we have different hybridization like sp3, sp2, and sp. So the sp, it's 1s, 1p, right? So 50%. 1s, 3p, that is 25% of s character. And because s character is closer to the nuclei, that means this bond is closer to the nuclei, so that means it's shorter, it's stronger. So that means the sp-CH bond is a stronger bond than the sp3-CH bond, which is a weaker bond, okay? This actually is a little bit advanced. So, but just keep that in mind. Okay, you can predict the bond strength by knowing what the hybridization of the participating atoms. The next concept I'm going to review with you is acid and bases. Okay, you know that the Bronsted acids, right? It's a proton donors, and bases are proton acceptors, Bronsted. Okay, but a compound can have the roles of both acid and base in different reactions. Why is that? Not why is that? Let me show you an example. So, this is Bronsted acid, acidic acid. It can react with hydroxide anion, like potassium hydroxide, sodium hydroxide. It can deprotonate this hydrogen to become an anion, right? So this molecule, acidic acid, acts as an acid, right? But it can also react with hydronium, okay, and to protonate this oxygen. So now in this reaction, this hydronium acted as an acid because it donates proton, right? It put one proton into the oxygen here. So in this reaction, it acts as a base. So actually, if you learn later, you will see that both of these steps are real steps that are in very important reactions. So normally, if you want to methylate or alkylate this oxygen, you need to add a base to deprotonate it first. Okay, if you want to do an esterification and you want to catalyze it with a proton with strong acid, it usually goes this way because it will activate the oxygen by putting a proton on it. Now it becomes more electrophilic. I know to some of you this is not familiar, but you will learn later. But you have to keep in mind, an acidic acid may not be a real acid in the reactions. Whether it's an acid or base really depends on the reaction conditions and what kind of reactions it is in. Oh, I just said that. Okay. And then we have the pKa. The concept of pKa is the measurement of acidity, which is also called acid strength. Okay, so this is calculated by this equation, and the equilibrium constant, the log of that, the minus log of that is the pKa number. So you already know that lower pKa means stronger acid, and higher pKa means weaker acid. Okay, you can see here. So if you have acidic acid, you react with NH3, you get the ammonia, and it's a weaker acid because the pKa of the ammonia is 9.4, which is weaker, and this one is also the same because this is a weaker acid, so this is stronger acid, and what you already know is that reaction equilibrium always favors the formation of weak acid because if you react with acidic acid with ammonia, it goes to the right. You can see the arrow here, right? Because this is the weaker acid. But if you react with these two, it's an equilibrium, but the equilibrium is towards the left because the pKa of the ethanol is higher than the pKa of this ammonium salt. So it goes to the weaker acid, which is ethanol here. So another concept is called conjugate base. Okay, the definition is that when an acid loses a proton, its conjugate base is formed. So you have acidic acid, its conjugate base is this anion, okay, which is acetate, what we call it. And if this is ammonium salt, which is 4 hydrogen, which has a proton to donate, this is the acid. This is the base. So if this base accepts a proton, it becomes its conjugate acid. So acid, conjugate base, base, conjugate acid. Keep that in mind. Okay. So why is the conjugate base concept very important? Is that sometimes you don't have the data of pKa, so you cannot compare what's more acidic, right? So sometimes you can just predict, but now with the concept of conjugate base, you can predict the acidity of the acid by looking at its conjugate base, okay? So if the conjugate base is very stable, then the acid is very strong, okay? This is a very good way to predict the acidity of something. Oh, so the stability of the conjugate base is an indicator of the strength of acid. So now I'm going to show you some trend, okay? So from the left to the right of the periodic table, so the electronegativity increase, which means the atoms on the right absorb the electron density stronger, okay? And from the top to the bottom, so the size of these atoms increase. So how does these properties affect the acidity? So because the electronegativity increases, so the fluoroanion, the F minus is more stable because it's more stable with more electrons because it's absorbed electrons strongly, right? So that means if the F anion is more stable, the HF is a stronger acid, right? Just as I talked in the previous slide. So from the left to right, so CH bond, NH bond, OH bond, HF. So HF is apparently more acidic than all these CH bond, NH bond, OH bond. Okay. And then the acidity of the from top to down also increases. Why? Because the anion of because the iodide is bigger. So if you have a bigger atom, a bigger nuclei, so the electron around the nuclei can disperse in a larger area. So if the electron is concentrated in one place, it's very unstable because it's high energy. It wants to react with something, right? But if the anion, the electron is dispersed in a larger area, like a big atom, like the iodide anion, so it's more stable because it's less reactive. So based on this, because the iodide anion has a larger space to disperse the electrons, so it's more stable, which means the conjugated acid, which is HI, is more acidic. So acidic. So that means from HF to HI, the acidity increases. Okay. So from all these charts, you can know that HI is actually a very strong acid. So what causes this stability, as I briefly mentioned in the previous slide, is that several effects. The first is that the inductive effect. So inductive effect is described as the polarization of a second bond due to electron withdrawing or donating effect of groups or atoms adjacent. So if you compare with this acetic acid, which has 3 hydrogen substitution, and you have a bromoacetic acid, which has 2 hydrogen, 1 bromide, right? And you want to know what's the difference of acidity. And you look at the conjugated base stability, right? Because this anion and because of the electron withdrawing effect of the bromide, so the minus is actually withdrawn into the bromide. So the minus charge is dispersed along this sigma bond. So which means the anion is more stabilized because the electrons is dispersed in a larger area, right? And but if you have 3 hydrogens, the effect is less obvious. And in this case, this is less stable. So, and because the anion, the bromide and a bromide containing anion is more stable than this, the acidity of the bromide substituted acetic acid is higher than this. And you must know that the inductive effect only happens through sigma bond, okay? It have to be connected by the single bond here, okay? So, so let's compare these. So we have a hydrogen. We already know the bromide is the bromide. This compound is more acidic. But how about the fluoride? Because the periodic table fluoride is on top. It's higher than the more upper than the bromide. So it means withdrawing electrons are stronger. Okay. So that means that the anion is more stable, which means the fluoride containing acetic acid is more acidic than chloride, than bromide, than H. Okay. And the distance also plays an effect. So if the fluoride is closer to the oxygen, it means it's the electron puller is closer to the active side, right? So the anion is pulled stronger. So that means the acidity of this OH bond is stronger than other compounds with fluoride further away. Basically, so if you imagine you have a super long, like let's say 100 carbon chains, if the fluoride is at one end and the carboxylic acid is on the another end, so the effect is quite small, right? If it's really close, its effect is stronger. So quite plain to understand. Another thing is called another thing that affects the stability of conjugate base is called the electron delocalization. So, so the fact is that acetic acid is a stronger acid than the ethanol. And if we compare the stability of their conjugate base, so the acetic acid conjugate base is actually shared with two oxygens. So you can draw resonance structures, which you have learned in general chemistry. Okay, you can the oxygen, the anion can jump into another oxygen here, and if you have if you see the electron density chart here, so the red one is the electron density. So you can see the minus is dispersed around the two oxygens, but for the ethanol anion, ethanolate, so the oxygen, the negative charge is only dispersed in one oxygen. So that means this anion is more stable, and its conjugate acid, which is acetic acid, is more acidic than the ethanol. Okay. So another concept that is you probably are learning it now instead of in general chemistry, it's called Lewis acid. Oh, you probably should already have learned that. So different from Bronsted acid, Lewis acid are electron pair donors, but you already know that if it's Bronsted acid, it's donating protons when it's accepted with an electron pair, right? So this statement is true that all Bronsted acid or base are Lewis acid and base. So what's a typical Lewis acid is shown here. So you have a trichloride aluminum, very useful catalyst or reagent in organic synthesis, and it can actually react with diazo ether with the oxygen. So the oxygen donate a pair of electrons to the aluminum. The aluminum accepts that pair of electrons, and these two form a complex together. So we call the aluminum, which accepts the electron pair, Lewis acid, and for the diazo ether, which donate electrons, the Lewis base. Okay, just keep that in mind. Okay, now we moved from the general properties of the organic molecules, and with all the reviews of the acid and base and the bond strengths, we move into the formal part of this course, which we will talk about the properties of alkanes first. So just a brief introduction for alkanes. So you have a linear alkanes, which is a CH4, and ethane, propane, which is drawing skeleton structures. You have to be familiar with these kind of drawings. And a general formula of linear alkane, and with N carbon atoms, you have 2N plus 2 hydrogen atoms. Okay, it's easy to understand because you have two hydrogens inside the chain, right? Each carbon have two hydrogen. At the end, you have two hydrogens and one to finish the chain, right? So you have 2N plus 2 at both ends of the chain. And alkanes can have side chains, okay? For a 4-carbon alkanes, you have butane, 2-methylpropane, and that's it. But if you allow ring structures, it now has more diversity. So you can put this end and this end together. You can have cyclobutane, what we call. And if you put this end, the middle, and this end together, you have methylcyclopropane. And the more extreme situation, if you put this carbon and this carbon together, you have very strange structures, which is called bicyclobutane. Okay? And then you have, let's say, the 5-carbon alkanes. You have pentane, 2-methylbutane, 2,2-dimethylpropane. Okay? That's without any rings. And if you are interested, you are welcome to figure out how many alkane structures with rings can C5 afford. Okay? For the C4, we have 3. It is a good guess that the C5 have more structures with ring structures in it, right? And with these particular structures, do you think it, so if you are interested again, can this be synthesized? So you can just search bicyclobutane and find out on Wikipedia. So it's beyond the requirement of this course, but again, when I read the Wikipedia of this molecule, it's quite interesting to me. Okay. All right. Then when we talk about the alkanes' physical properties, we have 3 things. So one is boiling point, melting point, and solubility. So how do you predict and how do you explain the properties of these alkanes? So for the boiling point, so if you have a greater intermolecular attractive force, which we'll talk about later, so you have a higher boiling point. So for the melting point, besides the intermolecular attractive force, you have the symmetry of the molecule actually is important, because the melting point is when the compound become transit from the solid to liquid, right? So with solid, it has a crystal structure in it. So actually, how those two crystals pack with each other is now very important for the melting point, because you can imagine that if those molecules pack really tight, it's really hard to break them apart, right? And for the solubility, so one simple sentence, like dissolves like, and we will talk about this. So what's the intermolecular attractive force mentioned here? So usually there are three kinds of them. One is van der Waals forces. One is the dipole-dipole interaction and hydrogen bonding. So remember here, hydrogen bonding is actually one kind of dipole-dipole interactions. I will mention this again. So van der Waals forces. So alkenes are non-polar molecules because they are all CH bound, right? There is no polar things in the alkenes. So they don't have a dipole-dipole interaction because the molecule, it's a C versus C, carbon versus carbon. So they are the same. So there are no dipole. No one is extracting electrons from another one, right? But they have induced dipole-dipole interaction. What that means is that although they don't have internal dipole, right? But one molecule interact with each other, it will induce a dipole, like very weak, but still some dipole, which is induced. We call it induced dipole. So here, so this helps them. So if this has some induced plus, then this will have some induced minus, and then it will react with, it will pack with each other, have this kind of intermolecular attractive force. Okay, then so. One rule is that the greater the surface area of the alkane, the higher the boiling point. The thing is very easy to understand, because if you have more surface area of the alkane compound, it can interact with each other with more area, right? So if you look at the trend here, so the methane's melting point is minus 167 degree, but octane is 125 degree. So that because octane is a long chain with 8 carbon, it has more surface area. So it can react with another octane with also a large surface area together. Then they have induced the dipole with them, like between them, so they can pack tightly, and so their boiling point is higher. Okay. And now but when we talk about the melting point, it's a different story, because remember, the packing ability now is taken into account. So look at this unpentane and the neopentane. The boiling point, the unpentane is higher than the neopentane, because unpentane is a long chain with more surface area. But the neopentane, it's like a ball, right? It's small, because all the carbon are attached to one carbon. It does not have a lot of surface area. But if you compare their melting points, the trend reversed. Now the neopentane has a higher boiling point than the normal pentane. That means in solid state, neopentane is harder to break apart, to melt. Okay, that's because although unpentane has greater surface area, neopentane has great symmetry. What that means is that this is a really rigid structures, right? Because it's very packed, and one carbon substitute 4 carbon. But this is a rope. You can consider it as a rope, right? So rope is really do not have great symmetry. It moves around like whenever it makes it happy, right? But this is a very rigid structures. So because it is rigid, it packs more tightly. So which means it has a higher melting point. Okay. And so when we were talking about that alkane is not polar molecules, so they only have induced dipole-dipole interaction, right? But if the alkane is substituted with some hetero atoms, okay, like fluoride or oxygen, now because the oxygen is different from carbon, and the fluoride is different, and also because the fluoride and the oxygen are really electron withdrawing atom because of higher electron negativity, right? So now it has dipole in it, okay? Carbon doesn't, but carbon fluoride, carbon oxygen, carbon heteroatom has dipole, okay? So now within the molecule, the negative charge is accumulated in the fluoride, in the oxygen, okay? Now the molecule can be drawn like this because it has internal dipole. And the positive part interact with the negative part is like magnets, right? And then you have a dipole-dipole interaction within the, like between these molecules. And as I said, dipole-dipole interaction are much stronger than the induced dipole-dipole, which is called van der Waals forces, okay? And those dipole exist because these alkenes are substituted with electron-negative atoms like fluoride or oxygen. So what's the effect? So if you have a cyclopentane, the boiling point 49 degrees, and because all carbon, they don't draw electron from each other, okay? So they only have the van der Waals forces, okay? But for the tetrahydrofuran, you have an oxygen, right? Now the oxygen is electron negative. It draws electron from the carbon near it, and it have dipole now. And because it has dipole, it has dipole-dipole interaction. And besides the van der Waals forces, the dipole-dipole interaction makes the interaction between these molecules very strong. So its boiling point is higher than the cyclopentane without any heteroatoms. So that means that this molecule, because due to the stronger intermolecular attractive force, it's higher to break apart and to boil it into a gas state, okay? Another example is that you can see if you have Y is H, so compare with you have a heteroatom in it, you can see the boiling point. I think the boiling point is higher than without any heterocycles, right? And this trend is true for every chain here. So the last one I'm going to introduce is the hydrogen bonding. So you probably already know what's hydrogen bonding, right? For water, you have the oxygen and the hydrogen. Oxygen draws electron with the dipole with minus here, and it attracts with another hydrogen here. But so, for example, the water, because they have oxygen in it, it has a hydrogen bonding, and because of the hydrogen bonding, its boiling point is much higher than methane, right? That's all. The hydrogen bonding is also responsible for the stability of life, right? Imagine if you don't have hydrogen bonding, the boiling point of water is minus 100. We don't exist, right? So one thing is that, keep in mind, hydrogen bonding is in its nature a dipole-dipole interaction. So you have a dipole here, you have dipole here, it interacts with each other. But the dipole-dipole interaction of a hydrogen bonding is much stronger than other dipole-dipole interaction, okay? So when you, in the future, you want to compare the the boiling point of two compounds, try to look for the hydrogen bonding first, because if there is hydrogen bonding, the boiling point is gonna be much higher than those molecules without hydrogen bonding. Okay, the solubility, one simple sentence, like dissolves like, non-polar compounds dissolves in non-polar solvents, polar dissolving polar solvents. So particularly important is with water, okay? Because water is a polar compound, right? We just talked about it. It has hydrogen bonding, and all these dipoles are interacting with each other. So when we say the compound is attracted to water, we call it hydrophilicity or hydrophilic, yes. And if it's repelled by water, it's hydrophobic, okay? This is important, especially when you try to learn some biochemistry. There is some interactions and which kind of molecule dissolves, which kind of molecule doesn't dissolve, and just keep that in mind. And this is an important chart. So you can see both of them, all of them are ethers, but the difference is that all of them have one oxygen while the carbon chain increase. So we can say with the carbon chain increase, more nonpolar component exist in the molecules, right? So that means nonpolar means hydrophobic. So from 2 carbon to 6 carbon, the molecule become more hydrophobic. It hates water, okay? So when it hates water, it becomes insoluble. So basically, dimethyl ether, it's soluble in water, okay? But when you increase the carbon chain to 6 carbons, it's insoluble. All right. So after the another important properties of alkane is that it has stereochemistry. Okay, this is probably a very new concept for you. So the stereochemistry deals with the shape of molecules and the properties of different shape of molecules. What does it have on the actual properties of the molecule in large? Okay, so there are several stereoisomers. First, no, there is one concept you already know, which is called a constitutional isomers, right? For the C5H12, so they can have a different bond connectivity as we talked before. You can have pentane, one substitution, two substitution, and you can have ring structures, right? I ask you to do it yourself, right? So you have ring structures. So these are isomeric compounds having different bond connectivity. But for the stereoisomer, it's isomeric compounds having the same bond connectivity, okay? But different three-dimensional orientation. What does that mean? So you have these two molecules. It has a 5-carbon chain, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same bond connectivity. One carbon attached to another, then another, 5 of them. But they have different three-dimensional orientation, okay? You can see, you will learn this later. This carbon and this carbon, they are on the different side of this double bond, right? While this carbon and this carbon, they are on the same side, okay? Although they connected very in the same way, but their shape are different. Let's look at these two. Connectivity, the same, carbon, 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 4 carbon with a phenyl ring, right? But if you put these chain on the paper, this carbon is pointing to you, but this carbon is pointing away from you, right? So they have the same bond connectivity, but different shape. What we know is that we call it S or R, and for this, we call it E and Z, which is a bigger part of the stereochemistry you are going to learn. Okay, so we are not going to learn immediately about the E and Z, S and R, but we are going to learn about some stereoisomers of alkanes. So we'll learn this later. And the stereoisomers that result from the rotation of the second bond is that cause the isomerization of these alkanes. What does that mean? So because the CC bond, right? If you rotate this CC bond, nothing happens. The bond is still there because it's a sigma bond. The definition of sigma bond is that it has an axial of symmetry, right? So you rotate it, the bond doesn't break, okay? But when you rotate it, it has consequences. So there is a roadmap of study because we already talked about the methane. But if you rotate this sigma bond, nothing happened, right? Because this is a hydrogen, nothing happened, yes. But for the ethane, you have a CC sigma bond. Now, because you can rotate this, when you rotate this, these three hydrogens change place, right? Change its place, rotate, and then its place relative to this 3 CH bond changes. Then we are going to go into more difficult, the butane structures, which have 3 CC bond. And finally, we are going to have the ring structures. And the ring structures, we will talk about this. You cannot rotate the CC bond here because singly, you cannot only rotate the CC bond because it breaks. It's a ring structures, right? You cannot twist it. But it will do something called a ring flip, which is quite interesting, and you should learn it. Okay, so molecular models are really important to study the stereochemistry. Actually, and there are 2 ways you can practice using a molecular model. So at the chemistry building 607, there is some models for you to use. So you are free to use, but don't take them away. It's shared. And you can also purchase them from the office. So I would say if you are really interested in organic chemistry or chemistry at large, you really should buy a model. Yeah, model set. So there are toys for organic chemists, and they really help solve a lot of questions. And some of the Moodle problem set, they require models to help you do it. And also some problems, if you have models, it's really straightforward. Okay, and I have my own models, which I will use during the class later. And so, yeah. Okay. Also, we have 10 minutes left, so I will just go slightly into the async part, okay? So async exists as many conformers because conformational isomers, which we call the conformers, because as I said, the CC bond can rotate, right? So you can see here, this hydrogen and these two hydrogens are in this kind of position, right? And if you rotate this clockwise, now this hydrogen and these two hydrogens, they are in different place. So their relative positions has changed, okay? And you can imagine the second bond can rotate 360 degrees or all the way, right? So these positions can change to any positions, and so there are the async as a result exists as many conformational isomers, okay? So if you recall that we can visualize 3D structures like this methane into 2D papers. So this bold CH bond pointing to you, the dashed CH bond point away from you. But the question is, for async, do we still need to draw like this? Or is there any easy ways to draw a async conformation or other alkanes conformations on a 2D pages? So what we are going to teach you is that we have a way to draw this. It's called a Newman projections, which is the best and the most clear molecular representation for discussion conformational isomers. So what does that mean? So for async is like here, right? We have 6 hydrogens. So I marked hydrogens on this carbon blue, and I marked the hydrogens on this carbon red, right? So to draw the Newman projection, you need to look through this direction. So look through this CC bond from this direction. Put your eyes here, okay? Put your eyes here and look at this direction. Now I have to show you the 3D model for that so you can understand it easily. Okay, so this is the model, you can move it around. Okay, so this is the C1, C2, right? The red, blue. What I want you to look through is this direction, okay? See? So look through this CC bond. So you can have so these 3 red hydrogens are in the front, 3 blue hydrogens are in the back, right? Understandable, huh? Okay, let's get back. Oh, see, it becomes like this. It becomes like this, and so we are going to draw this. So once we determine that we look through one CC bond, we can draw this. So the method is as follows. So front carbon is a dot, real carbon is a circle. Draw this, okay? So this dot is the front, this circle is the back. And the bonds at the front carbon are lines emanating from center dot. 3 red hydrogens, right? Is exactly like what we see, okay? Then bonds at the real carbon are lines going to the edge of the circle. So for the next bond, you don't draw from here, you draw from here, okay? Exactly, huh? So the hydrogen from the edge of the circle. See, that looks exactly like what we have visualized on my software, right? Okay, so since now we can draw them, so what are the conformers of async? So we have 2 representative conformers. One is called staggered, and one is called eclipsed. Okay, the staggered is like what we saw here. So all these bonds are equal distance. If you look at this direction, equal distance from each other, right? And the eclipse is that, so I have to show you in my 3D again. Okay, so this is the async with the eclipse structure. So you can see all those hydrogens are paired up, right? And if you look through this direction, again, C1, C2. Oh, here, yeah. Oh, see? The red one basically blocked your visual to the blue one because they are eclipsed. Huh, easy to understand. Let's go back. So to draw this, we already tried, right? That's called a staggered conformation. 6 CH bonds equidistant from each other. This. Okay, and to draw eclipse. So because we still want to show the back substitution, right? We don't want to. So if you don't draw the back, how do you know what's in the back, right? So what we do is that we still draw the hydrogen here, but we put the hydrogen very close to the red one here. So it's like, so this is called eclipse Newman projection. So basically, if you draw like this, we know that the hydrogen is eclipsed together. So all 6 CH bonds stacked on each other. Okay, this is these two are two extreme conformers of hexane. So this equidistance, this all stacked. So the conformers in between is that this red and this blue are away from each other, but the distance are different. You can see this distance is smaller than this distance. Okay, this is all the conformers in between these two extreme examples. Okay, but how do we know? How do we quantify the relationship between these CH bonds? So we say this equal distance to each other, but what do you mean by equal distance, right? So we introduce a concept called a dihedral angle. Okay, so this is an eclipse conformation, right? The hydrogen and this hydrogen are away from each other. This hydrogen and this hydrogen are stacked on each other, right? So we need to rotate this sigma bond. So this blue, green hydrogen is eclipsed with the red hydrogen. So the dihedral angle is the angle that needs to be turned about the CC bond. So this bond has to turn to make the two substituents eclipse to each other to make the green one into here. Okay, so that's what we call a dihedral angle in a conformer. All right. So now let's go back to the two extreme conformers here. So in order to turn this red CH bond eclipse to this blue CH bond, how many degrees do you have to turn? 60, right? Because they are equal distance. You divide 360 degrees by 6, it's 60. And how about this CH bond to this CH bond? 180, right? Because it's opposite to each other. You have to turn 180. Okay. But for the eclipse, they are already eclipsed to each other. So you don't have to turn anything, right? So the CH bond already stacked. So that means the dihedral angle, you don't have to turn. So you have to turn 0 degrees to make this red eclipse with this blue. But if you want to turn this red into this blue, you have to turn 120 degrees, right? So, okay, it's time to, so based on the Newman projections, you would know that the hexane exists in different conformers, and they have different degrees, right? And the degrees actually have consequences in the energy of these conformers. So you would say, so for you don't want to be so crowded in a room, right? So it's the same for hexane. So this red hydrogen really doesn't want to be that close with the blue hydrogen. This is very comfortable, right? Everybody is away from each other, but this is very strained, right? It's crowded. So that means that energy-wise, it's different. And from next lecture, I'm going to show you what's the energy difference and how do you predict the energy difference? How do you calculate these energy difference between different conformers? And after we finished with hexane, we are going to go deeper into a more complex molecule like the butane. And the butane, because there are more substitution, so more complex. And eventually we will go to the cyclohexane, which is a ring structures. And so before next lecture, I would recommend you to read through the chapter 1 and 3 of the book, and to sign up for the tutorial section. And if you have any questions, email me, email the tutor, and you can the office hour this Friday, so after next lecture. So just email me and the tutor if you have any questions. Okay, and so. I hope you learned something here because most of it is reviewing, but we are going to have some fun for the rest of the semester, okay? So I will stop here and hope you have a very good semester. All right, see you next time. Oh, if you have any questions left, I will stay for like 10 minutes so you can chat with me, okay? Oh, and also the slides